Good afternoon, everyone. Welcome back to E304. Today we're going to continue our discussion of the mechanics of oscillating atoms, and we're going to focus on the quantum behavior. So last time we talked about the classical description of two atoms as two masses on a spring, and we talked about the Lennard-Jones potential. And let's remember the Lennard-Jones potential looks something like this. Where there is some equilibrium x that is a minimum energy separation between two. Remember, we have two atoms connected by, or two masses connected by a spring. So from this model we came up with a few equations for potential energy, for kinetic energy, and for the natural frequency. Let's focus a little more on this area around x is equal to E, because really this is the area of interest for us. So let's look at that approximation. So if we have x, the direction x on the x-axis, we have potential energy on the y-axis. Let's just look for a moment at that area. Let's assume that the 0 point here is where xe is equal to 0. So we're just focusing in on the area right around the equilibrium there. And if we look at the Lennard-Jones potential around there, it looks something like a parabola that then goes off to do something like this. Well, if we look at our equations for potential energy that we derived in the previous lecture, we see that that potential energy was estimated as 1/2 k x minus xe squared. This is from the last lecture. So if we plot this potential energy, 1/2 k x minus xe, where xe is equal to 0, xe is equal to 0, then what we have here, let me use a different color, what we have here is a parabola. I'm going to draw them next to each other. A parabola looks like this. So you can see that right around the origin here, in this area of particular interest, the two approximations, the Lennard-Jones potential and this equation for potential energy, match quite well. So it's a good approximation to use for our purposes here. So looking at this, there's a few things that are a little bit surprising in terms of the quantum mechanics of this system. This equation, as we can see and as we've drawn here, is a continuous function. But we know that quantum harmonic oscillators should only have certain energy levels that are allowed. So quantum harmonic oscillator should only have certain energy levels that are allowed. So that they should be quantized. And the Lennard-Jones model here and this potential energy equation shows us a continuous function. So this can't be realistic for our description of the atomic behavior. So let's look at what is really happening in this case. Okay. So let's start with Heisenberg's uncertainty principle to get a better understanding of what we have here. So we remember Heisenberg's uncertainty principle tells us that the uncertainty in position times the uncertainty in momentum is greater than or equal to h bar over 2. So we learned this in the previous chapter, where of course h bar is equal to h over 2 pi. Okay, so this of course tells us that if we know the momentum or velocity exactly, we have no idea of the position, and the other way around, if we know the position exactly, we have no idea about the momentum. So based on this understanding, we can say that momentum can't be exactly 0 either. That would be an exact number, and we know we can't know it exactly. So the lowest energy of the system really exists where neither speed nor position are exactly 0. So what is the minimum energy level? What is the minimum allowed energy of this quantum harmonic oscillator that we're looking at? Well, how do we find that? Well, let's look at the equation for energy. So energy is going to be potential energy plus kinetic energy. Okay, so we know that kinetic energy is 1/2 the reduced mass, remember the reduced mass concept, times the velocity squared, and the potential energy is 1/2 the spring constant K x squared. So these equations we derived last lecture. Now we also know that velocity is related to momentum and mass. So V is equal to the momentum divided by the reduced mass. And we know that the natural frequency omega n is equal to the square root of K over the reduced mass. Okay. So knowing these parameters, we can simplify this energy equation a little bit. So E is equal to 1/2 the momentum P squared over the reduced mass, and plus 1/2 of the omega natural frequency omega n squared times the reduced mass times x squared. So now we have energy in terms of momentum P and position x. We use these two equations to plug in. All right, well, we know that we have some uncertainty in x and some uncertainty in p, so instead of p and x, we really want to be looking at delta p and delta x. So energy is, in fact, 1/2 of delta p squared over the reduced mass plus 1/2 of omega sub n squared times the reduced mass m sub r times delta x squared. All right. So from here we use Heisenberg's uncertainty principle. We use the fact that delta p is greater than or equal to h bar over 2 times 1 over delta x. We substitute that into the equation, and our final equation for E now becomes 1 over 2 mr times h bar over 2 times 1 over delta x squared plus 1/2 omega n squared mr delta x squared. All right, So this is our energy equation in terms of delta x, in terms of position. So what is the minimum energy? Well, if we have an equation for energy to find the minimum, what do? But we take the derivative. Take the derivative of the energy equation with respect to x. And we set that derivative equal to 0. Okay? So when we do that, we end up with, and I encourage you to do this on your own paper and make sure that you get the same result that I do. So we do dE dx and set that equal to 0, and you end up solving for delta x, and delta x ends up being the square root of h over 4 pi times the reduced mass times omega n. Okay? Now if you take delta x and plug into, so take this equation and plug into the energy equation, okay, we end up with an expression for the minimum energy, E naught, which is equal to h omega n over 4 pi, or it can be expressed in terms of h f n over 2. Okay, so this is our minimum allowed energy in the system. Well, what does this mean? So let's circle this. Let's keep this in mind. This is the minimum energy level that is allowed in the system. So what does that mean? So let me switch to a slide here that actually shows the allowed energy levels. So again, we draw here the potential, this parabola that gives us, that's 1/2 kx squared. So 1/2 kx squared, that's the parabola. And then we see that the minimum allowed energy is over here at E0, and it's 1/2 HFN. And now, if we remember from chapter 3, when we discussed these quantized energy levels, we know that the next energy level has to go up by a factor of HF. Remember that E, the energy of a photon that we've seen before, E is equal to HF. So the next energy level is HF higher than the first. The next one is 2HF higher. The next one is 3HF higher. So what does this tell us? Well, it tells us that the separation between the atoms here has some, there are some allowed energies for which this can exist around this equilibrium separation XE. And those energy levels that these atoms, the system is allowed to take on, are quantized in this way, and they exist in these levels. We can solve this equation in using Schrodinger's approach and using psi, the equation that we saw in chapter 3, the Schrodinger equation that we saw in chapter 3. And this is a fairly complicated derivation, but nonetheless, the solution comes out to be something very similar. And we can plot the wave function and the energy levels and wave functions according to the Schrodinger equation as such. So over here on the left, we see the wave functions. And on the right, we see the square of a wave function. So we might remember the square of the wave function tells us the probability of the system existing in that particular location. And the wave function here doesn't have a physical meaning per se. So the allowed energy levels are as seen here, and the wave function tells us that where the probability of the separation being between these two atoms, and you can see that it varies with the energy level. So finally, what we should see here is that looking at the probability of the system or the separation being a certain distance x. So if you look at the classical understanding, p of x is the probability here. So in the classical understanding, we know that if we had the ball on a spring like we talked about before, in our classical understanding, we know that the potential energy is highest at the most stretched out and most compressed area of the spring, and the potential energy is lowest when the spring is in its neutral position, because as it reaches a maximum, a most stretched out point, it's almost standing still right as it's switching to go back the other way. So in a classical sense, the probability is of finding the mass is greater on the outside, but we see that the quantum mechanical understanding tells us the exact opposite. At least at the lowest energy level. As we go to higher energy levels, for instance, n is equal to 2, we can see that this story changes a little bit, and there's some probability of finding this much separation or this much separation between the two atoms. And there's some probability that there's the XE separation. So as we go to really high energy levels, we see that the quantum theory comes closer to the classical theory. So the probability of finding the system in this state or this state over here becomes higher. So we can see that the quantum theory and the classical theory begin to merge at higher and higher energy levels, which should make sense to us.